Bismillahirrahmanirrahim. Dear students, from this week we will start a new method for plotting shear force and bending moment diagrams. The method that we have studied till this stage is a lengthy method for plotting shear force and bending moment diagrams, and it involves writing down of a lot of equations. We divide the beam into number of portions and then write down equation of shear and bending moment for each portion. We plug in some boundary conditions or limiting values, and then we get certain values and plot them to get the shear force and bending moment diagrams. But the next method that we are going to study today is a more direct method, and you will find that with a lot less effort we can end up with the same SFD and BMD if we follow the procedure correctly. And this method is basically based upon the relationship between applied load, shear and bending moment. So first of all, we need to understand that what this relationship is, and then we will utilize this relationship to draw SFDs and BMDs. So let's start with a small derivation of the relation among load, shear and moment. And for this we will consider an imaginary or a hypothetical beam. Like we have just a simply supported beam and some imaginary loading is acting on that. We have an area load, and this area load is not a uniformly distributed load. It is just some just any variation of omega, and we are developing this relationship for a generalized case so that it remains valid for all the different cases that we will be dealing with in future. So we have a beam that is subjected to a distributed load and it is subjected to a point load. Now, in order to develop the relationship between load, shear and moment, we will consider a very small segment of this beam, and its length is dx. So this length dx is drawn here on a large scale in figure B. This is a free body diagram of the length dx. It's a differential length, extremely small length, and we have marked the shear and bending moments at both the faces of this extremely small length. So if we assume that the shear V is upward on this face and movement is in clockwise direction, then in order to achieve the balance, the shear will be in the downward direction on the other face and movement will be in counterclockwise direction. The variation in shear at this section is dV. So shear at this on this face of the segment is V plus dV, and the moment is M plus dm. Now this variation can be anything. It may be positive, it may be negative. Now we are just considering a very generalized case. And how much is the resultant of omega? If we have this dx length, then how much will be the area of this part of UDL? It will be omega into dx. So we know that for any area load, if we want to calculate the resultant of the area load, we need to calculate the magnitude of the area, and that will give us the resultant of that area load. And for this extremely small distance, we may take this inclined part as horizontal. So this area will then form a rectangle, and we know that area of rectangle is length into height. So omega into dx is the resultant of this area load. And how much will be the and what will be the location of this resultant? It will definitely act at mid length. If the total length is dx as marked here, then it will be acting at dx by 2 from this face as well as from this face. So this is the free body diagram of this small portion, differential element of this beam. Now let's try to develop some relationship between load, moment and shear. So if we apply for shear, we know that we always apply sum of vertical forces equal to 0. So if we apply sigma Fy equal to 0 in this case, let me zoom it out a little bit so that you can see the free body diagram as well as the equation in the same view. Okay, so if we apply sigma Fy equal to 0 here, how many forces are acting in the vertical direction? This V in the upward direction, then this omega dx is also in the upward direction, so it's also positive, and then this V plus dV is acting in the downward direction. So if we rearrange this and simplify this, and this should be equal to 0. So if we rearrange and simplify this expression, we get dV is equal to omega dx. Let's label this equation as equation number 1. Now in this case we have dV on the left side and we have dx on the right side. If you want to calculate the relationship between shear and omega, we will have to integrate it in order to get rid of the differential elements. On the left side we are taking derivative with respect to V, so we will define the limits of integral in terms of V as well. So let's say that V is V1 here, shear is V1 on this side and V2 on this side. So we'll integrate this expression from V1 to V2. And similarly on the right side we have differential, we are differentiating the expression with respect to dx. So the limits of our integral will also be in terms of x. So we are integrating this from x1 to x2. Now what will we get from the left hand side? Because there is no other expression, we have only dv. So when we will put the limits of the integral, we will get v2 minus v1 on the left side. And if you look at the right side, omega into dx. Now what is omega? If you look at this diagram, omega is basically a function of x. Means that as x is changing, the intensity of this area load is also changing. And you know that whenever we have any expression in terms of x and we take its integral, what do we get? Like every expression or every equation basically represents a line. For example, if I give you y is equal to x, this equation represents a line which is at 45-degree angle with respect to x-axis. Similarly, if I give you y is equal to 2x plus 3, it represents a line and we can plot that line. So this omega x means that we have omega that is a function of x. So it will be expressed in terms of x, and if we take integration of this expression over in between certain limits, then what will that integral give us? That integral will give us area under that curve. So this omega dx, the integral of this omega dx from x1 to x2 gives us the area of load diagram from x1 to x2. So on left side we have v2 minus v1, and on right side we have area of load diagram. What is this v2 minus v1? v2 minus v1 is the change in v, and this is equal to the area of load diagram. This is one of the important relationships that we will discuss today. Let's label it as equation number 2, and this relationship says that the change in shear is equal to the area of load diagram. Now what does this thing mean actually? It will become more clear when we will be solving the numerical problems. Whenever we need to calculate the change in shear between two points, we will see that how much is the area of load diagram between those 2 points, and that area will define the change in shear. Okay, and again at this point we are talking in terms of variables, so it might not be crystal clear to you, but I hope when we will be solving the numerical problems, these things will become very clear. So anyways, this is one of the important relationships, and we will be using this relationship all the time in the next several weeks. So keep this relationship in your mind. The change in shear is equal to the area of load diagram. Now if we reconsider equation number 1, and we rearrange it, we get omega is equal to dv over dx. Now what is dv over dx? I've got this from equation number 1. I've just kept omega on one side, and on the other side I get dv over dx. Whenever we integrate any expression, we get area under the curve, and whenever we differentiate any expression at a particular point, we get the slope of that curve at that point. So here in this expression, what we are doing, we are differentiating shear with respect to x. So if omega is equal to dv over dx, its physical meaning is that omega, or applied load, is equal to the slope of shear force diagram. If you remember, when we used to decide the slope of shear force diagram in case of VDL, every time we used to see that whether the magnitude of the load is increasing or decreasing, and we would decide the slope of shear force diagram accordingly. And I used to tell you guys that we will see this relationship in future. So that's the relationship we are looking at today. The magnitude of the applied load is equal to the slope of shear force diagram, and we have actually already used this relationship in our previous method as well, without knowing the background of this, but I think you guys are already familiar with this, and this is also an important finding of our today's discussion. So just let's label it as equation number 3. These two equations, equation number 2 and equation number 3, will be used to draw shear force diagram using the direct method. Now let's move to bending moment. For bending moment, we will consider the same diagram, and we will apply sum of moment equal to 0. Sum of moment can be applied anywhere on this figure. Let's consider an arbitrary point and call this point as point B, and take sum of moment about this point. We are keeping this discussion very general so that we are sure that these relationships are valid for any case. We are not defining these relationships for a very specific case. Rather, these are very generalized. We are talking in terms of V, M, dV, dm, and for moment center, again, we are considering a generalized point. Okay, so let's take sigma mb equal to 0 with the convention clockwise movement as positive. Now let me zoom out a bit so that we have the figure as well as the expression in the same view. Now what different movements are here? First of all, m, if we start from the left side, and m is in clockwise direction, so it is positive. Then this v, how much is the lever arm of v with respect to point B? It is dx, and it will produce clockwise movement, so positive v into dx. Then this omega into dx, it will produce movement about point B in clockwise direction, and the lever arm is dx by 2. So plus omega into dx by 2, and then this v into dv is passing through point B, so it will not produce any movement about point B. And then we have m plus dm. This is in counterclockwise direction, so it will appear as a negative term in this expression, and this is equal to 0. Now if we simplify this m will be cancelled out with this m, and omega dx into dx by 2. Dx is a differential element, extremely small element, and if we solve this expression, we get dx square. Square of differential elements are extremely small, and often we can neglect them in our calculations or derivations. So that's what we are going to do here. Like whenever we have square of any number that is smaller than 1, that square gives us a smaller number. For example, square of 2 is 4, and 4 is a bigger number than 2. But the square of 0.5 is 0.25, which is even smaller than 0.5. So if we have a differential element, its square is extremely small and it can be neglected. So we'll just cancel that term out here. So if we simplify this expression, we get dm is equal to dx, v dx. Let's call this as equation number 4. And in order to get the relationship between m and shear, we will integrate this expression. And this expression on the left side has a differential with respect to m. So the limits will also be with respect to m. Dm Okay, so we'll integrate it from m1 to m2, and on the right side we have dx, so the limits will also be with respect to x, x1 to x2. Now if we integrate dm from m1 to m2, we get m2 minus m1, and v dx is the expression for shear. And if we integrate the expression for shear from x1 to x2, we will get the area of shear force diagram from x1 to x2. So on the right side we get area of SFD, and on the left side we have m2 minus m1. And what is m2 minus m1? m2 minus m1 is the change in moment. So the change in moment is equal to the area of shear force diagram. This is another important relationship, and let's highlight it and mark it as equation number 5. This is one of the expressions that we will be using while drawing a BMD using direct method. Now let's consider equation number 4 again and rearrange this. We'll get V is equal to dm over dx. And as I said earlier, whenever we take whenever we differentiate any equation at any particular point, we get slope of the curve at that point. Every expression represents, like every mathematical expression represents a curve. If it's a single degree expression, it will represent a straight line. If it's second degree, it will represent a second degree line, and so on. So dm over dx, and if we integrate that expression, we get area under the curve. And if we differentiate that expression at any particular point, we get slope of the curve at that point. So dm over dx is basically the slope of bending moment diagram. So this expression says that V is equal to slope of bending moment diagram. If you recall, we have used this relationship in the past as well. Whenever we used to decide the slope of bending moment diagram, we would look at the magnitude of shear force diagram. So if the magnitude of shear force diagram increases, the slope of bending moment diagram should also increase, and vice versa. And this expression will also be used while applying the direct method for plotting of SFD and BMD. So the 4 most important expressions from this discussion are expression number 2, that the change in shear is equal to the area of load diagram, and the slope of SFD is equal to the magnitude of load. And then equation number 5, that says the change in moment is equal to the area of shear force diagram, and expression number 6, that says that the magnitude of shear is equal to slope of bending moment diagram. So using these 4 relationships, we will draw shear force and bending moment diagrams, and we will solve some problems in this week. So I will just stop recording here for the derivation here, and I will make separate clip for the problems using this direct method of plotting shear force and bending moment diagram. So thank you very much.